February 9th, 1945. A flak battery outside Magdeburg, Germany. Obergefreiter Hans Keller crouched beside his 88mm gun as American B-17 seconds droned overhead at 23,000 feet. His crew had fired 214 shells that afternoon, their fuses meticulously set to detonate at calculated altitudes. By his count, they had seen perhaps 4 bombers trail smoke, maybe 2 went down. The math was crushing. At this rate, his battery expended roughly 50 shells for every hit they scored on an American heavy bomber, and a hit didn't mean a kill. The fortresses could absorb tremendous punishment. Keller watched empty brass casings pile up around his position and felt the weight of futility. What he didn't know, what his commanders didn't know, was that American Navy gunners facing Japanese kamikaze attacks in the Pacific were achieving something his Wehrmacht training had taught him was impossible. They were hitting aircraft with nearly every shell they fired, not through superior aim, not through better training, through technology that rendered aim almost irrelevant. The story of how American proximity fuses created a revolution in anti-aircraft warfare, while German gunners remained trapped in obsolete tactics, begins not with artillery theory, but with a simple mathematical problem that every military power in the world had concluded was unsolvable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The National Defense Research Committee, formed on June 27, 1940, brought together America's leading physicists under Vannevar Bush. Among them was Merle Tuve, whose brilliant but volatile temperament would drive a team that eventually numbered over 1,000 scientists. Their mission was to solve what seemed like a contradiction in terms: create a fuse that could sense its proximity to a countermeasure, target and automatically detonate, using electronics sophisticated enough to make such detection possible yet rugged enough to survive being fired from a gun. Consider the engineering impossibility. When a 5-inch anti-aircraft shell fires from a naval gun, it accelerates from 0 to 2,600 feet per second in approximately 20 feet of gun barrel. This creates 20,000 times the force of Earth's gravity. Every component inside that shell experiences crushing force equivalent to being struck by a sledgehammer. The shell then spins at 25,000 revolutions per minute as rifling imparts gyroscopic stability. And after surviving this violence, delicate electronics containing miniature vacuum tubes, a complete radio transmitter and receiver, must function perfectly during the few seconds of flight time before reaching the target. Every engineer who examined the problem reached the same conclusion. The forces involved would pulverize anything sophisticated enough to detect proximity. If you made it simple enough to survive, it couldn't detect anything. If you made it sophisticated enough to detect, it would shatter on firing. Germany had explored proximity fuses as early as 1930, developing over 30 different designs. Engineers at Rheinmetall-Borsig tested acoustic sensors triggered by engine noise, electrostatic detectors responding to charged aircraft surfaces, even infrared systems attempting to sense heat signatures. By 1939, after nearly a decade of research, German scientists had concluded the technical challenges were insurmountable with available technology. The acoustic fuses picked up wind noise and friendly aircraft. The electrostatic systems couldn't detect targets reliably at combat ranges. The infrared sensors were blinded by clouds. Most fundamentally, none could survive gunfiring. Hitler's 1940 directive, prioritizing only projects that could reach production within 6 months, doomed whatever remained of German proximity fuse development. Resources shifted to more immediate weapons. The Führer needed tanks and artillery pieces for Operation Barbarossa, not experimental electronics that might work in 5 years. Britain reached further before hitting the same wall. Researchers at the Telecommunications Research Establishment conceived using miniature Doppler radar. They tested prototypes on unguided rockets, which faced far gentler acceleration than gun-fired shells. But British industry, already stretched to breaking by war production, couldn't manufacture the miniaturized components in sufficient quantities. More critically, they couldn't make vacuum tubes survive. The smallest tubes available, those designed for hearing aids, were still too fragile. By 1941, British scientists had working prototypes that functioned roughly 50% of the time under ideal laboratory conditions. For military use, a 50% failure rate was catastrophically inadequate. You can't defend a ship with ammunition that works half the time. Through the TISAD mission, Britain shared everything they'd learned with America. But it would be American scientists and American manufacturing capacity that actually made it work, not as a laboratory curiosity, but as a mass-produced weapon manufactured by the millions. Section T of what became the Applied Physics Laboratory at Johns Hopkins University, established March 10, 1942 in a rented Chevrolet garage in Silver Spring, Maryland, settled on a radio-based approach. A miniature transmitter in the shell's nose would emit radio waves at roughly 180 to 220 megahertz. When these waves struck a target and reflected back, the frequency would shift due to Doppler effect. When that reflected signal reached a predetermined frequency shift, indicating optimal range, an electrical circuit would close and detonate the shell. Elegant in theory, nearly impossible in practice. The fuse had to fit inside a 5-inch shell nose, leaving room for 7 pounds of high explosive. In that cramped space, engineers crammed a complete radio transceiver, a power source, multiple safety mechanisms, and a detonator. All of it had to function after months in storage, through temperature extremes from Arctic cold to tropical heat, and after the violence of firing. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942, faced developing what the team called rugged vacuum tubes. Standard miniature tubes designed for hearing aids sat gently in someone's pocket. Van Allen needed tubes that could survive forces that would crush steel. Working with Sylvania engineers, he redesigned tubes from first principles. Glass envelopes were thickened and carefully annealed to resist shattering. Internal filaments and grids were redesigned with shorter spans and heavier construction. The tubes were potted in wax inside the fuse body, cushioning them against shock. Testing was brutal. Complete fuses were fired from a vertical gun into soft earth at the Naval Proving Grounds in Dahlgren, Virginia. The earth caught shells gently enough that researchers could recover fuses and examine tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, tubes gradually achieved acceptable survival rates. By September 1941, they were succeeding above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. Engineers were confident they could improve reliability during production ramp-up. They were right. By early 1943, reliability climbed above 90%, but vacuum tubes were only one challenge among dozens. The fuse needed a power source. Conventional batteries were too large and degraded during storage, particularly in tropical heat. Engineers developed a reserve battery using liquid electrolyte kept separate from battery plates until firing. When the shell fired, centrifugal force spun electrolyte into contact with plates, generating electricity. This gave batteries indefinite storage life, regardless of climate. Safety mechanisms multiplied complexity. The fuse couldn't arm until well clear of the gun. It required protection against accidental detonation from radio interference or the ship's own radar. It needed suppression circuitry preventing premature detonation when fired at low angles over water where radio waves would reflect off the surface. Each safety feature added components. By development's completion, each proximity fuse contained approximately 130 miniaturized electronic components in a package 8 inches long, weighing just over 2 pounds. On August 12, 1942, light cruiser USS Cleveland conducted first operational testing in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, downing maneuvering drones typically required dozens of shells. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 bursts on the first day. The Navy immediately cancelled remaining scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture fuses: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly. By late 1942, factories produced 500 fuses daily, but American industrial capacity was just warming up. By late 1943, production reached 40,000 fuses per day. Over the war's course, American industry produced more than 22 million proximity fuses, at a cost exceeding $1 billion 1940s dollars. More than 100 factories participated in some production phase. Crosley Corporation in Cincinnati alone produced over 525,000 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days weekly, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts produced even more, manufacturing over 568,000 fuses, while also producing 95% of all miniature vacuum tubes used across the program. Thousands of workers, many of them women, assembled intricate components under absolute secrecy. Workers signed secrecy oaths and were searched entering and leaving facilities. They didn't know what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device received the deliberately misleading codename VT fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Even its combat use was initially restricted to situations where no chance existed of a dud falling into enemy hands. First combat use came January 5, 1943 off Guadalcanal. 4. Japanese HED. 3. Dive bombers attacked a U.S. Navy task force. As aircraft broke off their attack, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on cruiser USS Helena, fired 3 salvos of proximity-fused shells. All 3 salvos exploded near one bomber, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners achieved what would have required dozens of conventional shells. They downed an enemy aircraft without scoring a direct hit. Word of success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were shipping to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft, downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. Let that sink in. 1/4 of shells fired accounted for more than half the kills. The effectiveness ratio was revolutionary. Admiral Arleigh Burke, later Chief of Naval Operations, recalled that when serving as Chief of Staff to Admiral Mark Mitscher, commanding fast carrier task forces, proximity fuses knocked down enemy planes by the dozens. True effectiveness was demonstrated May 11, 1945 off Okinawa. 2 destroyers, USS Hadley and USS Hugh W. Evans, came under assault from approximately 150 Japanese aircraft during Operation Kikusui No. 6. Many aircraft were loaded with explosives, intent on suicide runs. During approximately 1 hour and 25 minutes of intense combat, the 2 destroyers and 4 support craft faced overwhelming odds. Hadley knocked down 23 enemy planes before being hit by 1 bomb, 3 kamikazes, and 1 Oka rocket bomb. Hugh W. Evans accounted for additional aircraft before being hit 4 times by suicide planes and left dead in the water. Both ships survived despite catastrophic damage. The verdict on proximity-fused ammunition in this action was indispensable. But for most of the war, the Pentagon strictly forbade using the fuse over land. Risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated bomber losses could increase by 300%. The strategic air campaign might become impossible. Fuses were used only over water, where dud shells would sink beyond enemy reach. When a dud proximity-fused shell landed on Sicily during the July 1943 invasion, Headquarters dispatched a special patrol to recover it before German forces could find it. This absolute security restriction began cracking in June 1944 when Germany unleashed the V-1 flying bomb against London. Launched from sites across the English Channel, Von II approached at speeds of 400 miles per hour, faster than many Allied fighters. Small, fast, arriving without warning, they were extraordinarily difficult to intercept. From June to late August 1944, Germany launched over 9,000 Von II against Britain, inflicting tens of thousands of civilian casualties. British defences initially could destroy only 17% of Von II entering the coastal gunbelt. The situation was desperate. Prime Minister Winston Churchill authorised using proximity fuses in anti-aircraft guns defending Britain. Modified fuses rushed into production, specifically calibrated for small, fast Von II. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and fire control computers. The effect was dramatic. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming Von II were shot down. Churchill later stated the proximity fuse made possible the successes anti-aircraft command was obtaining. The V-1 campaign demonstrated beyond doubt that the proximity fuse was war-winning technology. But it also meant the secret was partially compromised. Thousands of fuses were being fired over land. Risk that seemed unacceptable in 1943 now had to be weighed against military necessity. In December 1944, that calculation changed completely. On the morning of December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. Germans struck through the Ardennes forest, aiming to split Allied armies and capture the vital port of Antwerp. The offensive took Allies by complete surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. Weather was terrible with heavy snow and thick clouds grounding Allied air power. German commanders felt safe from artillery fire because poor visibility made accurate observation nearly impossible. They were catastrophically wrong. On December 16th, the same day the offensive began, Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received a new type of ammunition, proximity-fused shells, codenamed POSIT, but Supreme Commander Dwight Eisenhower had not yet authorized their use over land. The secrecy restrictions were still technically in place. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing air bursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 50 feet above ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Foxholes provided no protection. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. They couldn't hear the shells approaching due to high velocity. The first warning was the explosion overhead. Hans Keller, the flak gunner outside Magdeburg, would later encounter American proximity fuses from the receiving end during the Battle of the Bulge, when his unit was reassigned to ground defense. He described the experience in a post-war interview conducted in 1946. The shells came without warning. We heard no whistle, no incoming sound. Just explosions above us. Men were hit from above, in the head and shoulders. Our foxholes became traps. We tried to dig deeper, but the fragments came down at angles. There was nowhere to hide. What made it worse, Keller explained, was the consistency. With normal artillery, perhaps one shell in 10 would airburst if the fuse timing was perfect. Most shells hit the ground and their fragments spread horizontally. You could survive in a foxhole, but these American shells, every single one exploded in the air, every single one. We thought they had observation aircraft we couldn't see through the clouds, directing every shell precisely. We didn't understand how it was possible. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department describing an action near the Sauer River. His Third Army had caught a German battalion attempting to cross with a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction, "I am glad you all thought of it first." The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Panzer Brigade 150, part of the elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery, battalions supporting the defense, fired proximity-fused shells with devastating effect. The air burst so unnerved attackers that some charged directly into American positions, seeking any shelter from the overhead explosions. The attack was repelled by afternoon. German prisoners of war interviewed by American intelligence officers captured the psychological impact. One German artillery officer captured in January 1945 described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon. Not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt. But he immediately added, Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. What they didn't realize was even more disturbing. The technology killing them on the ground was the same technology that had been protecting American ships in the Pacific for 2 years. The same fuses, the same principles, applied to different targets with equal effectiveness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hans Keller's experience illustrates the German perspective perfectly. Throughout 1944, he had manned his 88mm flak gun, firing at American bombers with meticulously calculated fuse settings. His crew worked with mechanical precision. Spotters calculated altitude and speed. Crews adjusted fuses and elevation. The weapon fired rapidly, shell after shell timed to explode amid bomber streams. They were good at their jobs. Keller's battery was considered well-trained, experienced, efficient. They followed doctrine developed over years of combat. They achieved results consistent with other German flak batteries. By late 1944, German flak batteries averaged roughly 16,000 shells fired per bomber destroyed. Some estimates ran as high as 3,300 shells per kill, depending on the conditions and the specific period measured. These weren't failures of training or courage. They represented the mathematical limits of timed fuses and predicted fire. even with radar assistance, even with experienced crews. Hitting a maneuvering target at 23,000 feet with a shell that had to be fused to explode at precisely the right moment was extraordinarily difficult. The gunner had to predict where the bomber would be, calculate the shell's flight time, set the fuse accordingly, and hope the bomber didn't change altitude or speed. Meanwhile, in the Pacific, American 5-inch naval guns equipped with proximity fuses were achieving kill ratios of approximately 310 rounds per aircraft against kamikazes. Against conventional aircraft making bombing runs, the ratio was 624 rounds per kill. Not 16,000, not 3,000. 624 rounds. And many of those rounds were fired in defensive barrages, not precise aimed shots. The difference wasn't training. American gunners weren't more skilled than their German counterparts. The difference wasn't courage. German Flak crews showed tremendous bravery manning exposed positions under Allied fighter attack. The difference was that American shells didn't need perfect aim. They needed to get close. The proximity fuse did the rest. Consider what this meant in practical terms. A German 88mm flak gun firing at an American B-17 at 23,000 feet had to set its fuse to detonate at exactly 23,000 feet. If the bomber climbed or dove even 500 feet, the shell exploded harmlessly. If the fuse timing was slightly off by even a fraction of a second at those velocities, the shell missed by hundreds of feet. The German crew fired, hoped, and usually missed. An American 5-inch gun firing at a Japanese aircraft didn't need perfect altitude prediction. The proximity fuse would detonate whenever the shell passed within roughly 70 yards of any substantial metallic object. The bomber could be at 22,000 feet or 24,000 feet. The shell would still explode at optimal range for fragment dispersion. Aim became less about precision and more about getting the shell into the general vicinity of the target. This transformed anti-aircraft gunnery from a precision art into an area saturation problem. American doctrine evolved to maximize this advantage. Forward observers called down fire not just on visible targets but on suspected positions. Artillery batteries laid down barrage patterns covering entire areas. The proximity fuses meant every shell was an effective airburst. No wasted ammunition. No shells burying themselves harmlessly in dirt. Every round that left the barrel had maximum lethal effect. German tactical doctrine developed over years of warfare had to be completely rewritten. Traditional defensive positions were suddenly death traps. Moving in the open, during artillery fire, was suicide. The Germans tried to adapt by dispersing more widely and staying constantly mobile, but adaptation had limits. The proximity fuse fundamentally altered the equation. You can't disperse enough to avoid area weapons. You can't dig deep enough to avoid overhead bursts. German soldiers began exhibiting what American intelligence termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Some units experienced discipline problems with soldiers refusing orders to move into areas under American artillery coverage. Officers reported that veteran soldiers who had survived Stalingrad and Kursk were breaking down under the psychological pressure of facing weapons against which there was no defense. American intelligence reports noted German commanders were offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. By January 1945, Wright Field in Ohio had developed electronic countermeasure systems designed to jam the fuse's radio signals, based on the assumption that captured fuses would lead to German jamming efforts. But German engineers never fully grasped what they had captured. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, they looked at recovered American shell fragments and couldn't reconcile what they saw with what they believed was possible. Some German technical reports from early 1945 describe American shells with unusual fusing mechanisms, but attribute their effectiveness to superior radar fire control, not to the shells themselves containing active radio systems. This cognitive blindness was understandable. German engineers had spent the 1930s testing proximity fuses. They had concluded the technology was impossible with vacuum tube electronics. Even their most optimistic assessments suggested proximity fuses might be feasible by 1950 or 1955, after solid-state electronics matured. The idea that Americans had actually manufactured millions of working radio fuses, each containing miniaturized vacuum tubes that survived gunfiring, seemed absurd. It violated everything German engineers knew about electronics and artillery. Their expertise told them it couldn't be done, so when confronted with evidence it had been done, they rationalized alternative explanations. The Americans must have better aim, better radar, better fire control computers, anything except the impossible truth that every American shell contained a miniature radio station. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. Ground combat intensified as well. During Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe might have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defences, equipped with proximity fuses, might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. Technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch. Rheinmetall-Borsig developed an electrostatic fuse called Kuhglock using capacitive detection. There were optical fuses, magnetic fuses, and experimental radio fuses similar to the American design, but none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired. The Kuhglöckchen, a smaller version designed specifically for 88mm and 128mm flak shells, achieved impressive performance in testing. Initial tests demonstrated sensitivity of 1 to 2 meters and reliability of 80% when fired against a metal cable target. Circuit adjustments increased sensitivity to 3 to 4 meters with reliability approaching 95%. Further work showed 10 to 15 meter sensitivity. By all accounts, the German electrostatic fuse was nearly ready for production by early 1945. It was based on different principles than the American radio fuse, using capacitive detection rather than Doppler radar. This made it potentially resistant to jamming, unlike the American design. Some engineers believed it might have been even more reliable than the American fuse, being simpler mechanically and requiring fewer components. Series production was scheduled for March 1945, but by then it was far too late. Germany lacked industrial capacity to set up mass production. Even if production facilities could have been established, the resources required would have competed with production of tanks, aircraft, and basic ammunition. Germany in early 1945 was collapsing. Factories were being bombed, supply lines were cut, transportation networks were destroyed, raw materials were scarce. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse alone consumed over $1 billion 1940s dollars. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. Germany, fighting a multi-front war while being bombed around the clock, simply couldn't allocate such resources to a single weapon system. The production statistics were staggering in their implications. At peak output, American factories produced 70,000 fuses per day. That represents nearly 3 billion individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale. At $18 per fuse, the weapon was expensive but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness was an obvious value. The secrecy was so complete that production workers at different factories didn't know other facilities were building the same. Components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended, and the proximity fuse was finally revealed to the public. For German prisoners of war who witnessed the defense against WWII flying bombs while held in Britain, the revelation of what they had faced was profound. They could see anti-aircraft guns firing and Von second exploding in mid-air with disturbing consistency. They understood the same technology that had devastated their forces in the Ardennes was now protecting British cities. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production. It was a realization they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war, not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources Germany could not match. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century with outdated assumptions about what was possible. His worldview, built on German technical superiority and engineering excellence, had been shattered by a 5-pound device containing 130 miniaturized components that functioned flawlessly under conditions German experts had deemed impossible. The proximity fuse demonstrated multiple technological advances that would reshape the post-war world. Miniaturized vacuum tubes required breakthroughs in material science, particularly in glass composition and annealing techniques. The printed circuit boards were among the first mass-produced examples of a technology that would revolutionize electronics. The reserve battery design using centrifugal activation was innovative. The radio circuitry was elegant and efficient, but perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality required systems and processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that would become foundations of modern manufacturing. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes. James Van Allen, the physicist who helped develop the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer, one satellite launched in 1958, credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions. Modern weapon systems use descendants of the World War II proximity fuse. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys and operate in jamming environments. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The broader lesson extended beyond the proximity fuse to the entire character of American military production during World War II. America outproduced the Axis powers not just in quantity but in quality and sophistication. American weapons were not always individually superior. German tanks had thicker armor, German optics were often better, but American weapons worked reliably, were produced in overwhelming numbers, and included technological innovations like proximity fuses that gave critical advantages. The combination of quantity and quality was what made American production decisive. The proximity fuse provided a force multiplier that turned numerical superiority into overwhelming dominance. By the final year of the war, German forces were facing enemies who had better weapons, more weapons, and technological advantages that made traditional tactics obsolete. The casualty statistics reflected the impact. During the Battle of the Bulge, despite initial surprise and favorable terrain, German forces suffered disproportionate casualties. American artillery was responsible for an unusually high percentage of German losses. Medical personnel reported that wounds from proximity-fused shells tended to be more severe than wounds from traditional artillery. The shrapnel came from above, targeting the head and shoulders. Multiple fragment wounds were common. The lethality was significantly higher. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and characteristics. Without intact working fuses to analyze, German engineers could not determine specifications needed for jamming. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted. The sense of helplessness broke the will to resist. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing effectiveness of defensive operations. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft and ballistic missiles. These were impressive achievements but came too late and in too few numbers to affect the war's outcome. America invested in technologies that could be mass-produced immediately. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability. The result was a weapon available in overwhelming numbers when needed. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. In the final accounting, the proximity fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable. The German soldiers who faced proximity-fused fire understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The weapon that had seemed impossible to build became the weapon that changed warfare. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by the tens of millions. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.